NASA's James Webb Space Telescope has proven its unparalleled ability to study the atmosphere of a massive exoplanet more than 1,000 light-years away, realizing a remarkable dream for astronomers. Webb has discovered haze, clouds, and ambiguous water signatures in a single observation using the combined power of its 270T mirror, precision spectrographs, and sensitive detectors. These discoveries were previously thought to be impossible based on earlier observations. Webb's near-infrared imager and slit spectrograph were used to create the transmission spectrum of the hot gas giant WASP-96b, providing just a small glimpse into the mission's exciting future of exoplanet exploration. Learn more about these amazing discoveries made by the James Webb Space Telescope by watching towards the end of today's episode. A far-off exoplanet's steamy atmosphere is revealed by Webb. The water vapor signature in the atmosphere of a hot, puffy gas giant orbiting a far-off sun-like star has been captured by JWST. It also discovered indications of clouds and haze. The observation, the most thorough of its kind to date, shows off Webb's amazing capacity to study atmospheres thousands of light-years away. Based on small reductions in the brightness of specific colors of light, it indicates the presence of particular gas molecules. The Hubble Space Telescope has studied the atmosphere of many exoplanets over the past 20 years, detecting water for the first time in 2013. However, Webb's quick and more thorough observation represents a significant advancement in the effort to identify potentially habitable planets beyond Earth. There are more than 5,000 confirmed exoplanets in the Milky Way, including WASP-96b. It represents a type of gas giant that has no direct counterpart in our solar system and is roughly 1,150 light-years away in the southern sky constellation Phoenix. WASP-96b is significantly puffier than any other planet orbiting our Sun, with a mass less than half that of Jupiter and a diameter 1 or 2 times greater. It is also noticeably hotter, with a temperature of more than 1,000 degrees Fahrenheit. WASP-96b makes one orbit around its Sun-like star every 3.5 Earth days, orbiting so closely to it that it is only 1/9 the distance between Mercury and the Sun. WASP-96b is the perfect target for atmospheric observations due to its large size, quick orbital period, puffy atmosphere, and absence of contaminating light from nearby stars. On June 21, the WASP-96 system was observed by Webb's near-infrared imager and slitless spectrograph, NIRISS. The NIRISS observed for 6.4 hours as the planet moved across the star. The end result is a light curve that depicts the overall dimming of starlight during the transit and a transmission spectrum that shows the brightness variation of specific infrared light wavelengths between 0.6 and 2.8 microns. While the transmission spectrum reveals previously undiscovered details of the atmosphere, the light curve confirms properties of the planet that had already been established from other observations, including its existence, size, and orbit. The clear signature of water, the presence of haze, and clouds that, based on earlier observations, were believed not to exist are notable discoveries. The starlight filtered by a planet's atmosphere as it passes in front of the star is compared to the unfiltered starlight observed when the planet is next to the star to create a transmission spectrum. Based on the absorption pattern locations, heights, and peaks on the graph, scientists are able to identify and quantify the abundance of important gases in the planet's atmosphere. Atoms and molecules have distinctive patterns of wavelengths that they absorb, akin to how people have distinguishable fingerprints and DNA sequences. This unique feature allows scientists to identify and study various elements and compounds in different environments, including distant exoplanets. The James Webb Space Telescope, JWST, has leveraged this principle to conduct groundbreaking research on exoplanet atmospheres, offering unprecedented insights into their composition and behavior. WASP-96b's spectrum, recorded by Webb's near-infrared imager and slitless spectrograph, NIRISS, exemplifies the telescope's advanced capabilities. This spectrum not only contains the most accurate near-infrared transmission spectrum of an exoplanet atmosphere to date, but also spans a remarkable variety of wavelengths. These include visible red light and regions of the spectrum that have not previously been accessible from other telescopes. This comprehensive range of wavelengths is crucial for several reasons. Firstly, it allows for the detection of a wider array of chemical compounds and elements within the exoplanet's atmosphere. Different molecules absorb light at different wavelengths, and by covering a broad spectrum, JWST can identify and quantify these molecules with greater precision. For instance, water vapor, carbon dioxide, methane, and oxygen have specific absorption features that can be detected and analyzed through these spectral observations. The ability to observe in the near-infrared range is particularly significant. Infrared light can penetrate dust clouds and other obstructions that visible light cannot, providing a clearer and more detailed view of the exoplanet's atmosphere. This capability is essential for studying planets that orbit stars with substantial amounts of dust and gas, as well as for observing the atmospheric layers of the planets themselves. Furthermore, the inclusion of visible red light in the spectrum allows for a more holistic understanding of the atmospheric composition. Visible light can provide information about the presence of aerosols and clouds, which play a crucial role in the climate and weather patterns of the planet. By combining data from both visible and infrared wavelengths, scientists can develop more accurate models of exoplanet atmospheres and better understand their dynamics. The data gathered from WASP-96b's spectrum also offer insights into the planet's formation and evolution. By analyzing the relative abundances of different elements and compounds, researchers can infer the processes that led to the planet's current state. For example, the presence of certain isotopes might indicate whether the planet formed in situ or migrated from a different part of its star system. Moreover, this detailed spectral data enables scientists to estimate the temperature and pressure conditions within the exoplanet's atmosphere. These parameters are crucial for understanding the planet's potential habitability. By knowing the temperature and pressure, researchers can determine the likelihood of liquid water existing on the planet's surface, a key factor for the potential for life. The advancements in spectral analysis provided by JWST represent a significant leap forward in the field of exoplanet research. Previous missions, such as the Hubble Space Telescope, have laid the groundwork by detecting atmospheric features of exoplanets, but JWST's enhanced capabilities allow for much more detailed and comprehensive studies. The higher resolution and broader wavelength coverage of JWST enable the detection of finer details in the spectral data, leading to more accurate and insightful conclusions. One of the most exciting aspects of this research is the potential to discover biosignatures, indicators of life on other planets. By identifying specific combinations of gases that are typically associated with biological processes, such as oxygen and methane, scientists can pinpoint planets that might harbor life. The precise measurements provided by JWST are critical for distinguishing between biotic and abiotic sources of these gases. In addition to its scientific achievements, JWST's observations of WASP-96b also demonstrate the technical prowess of the telescope. The ability to record such a detailed and comprehensive spectrum is a testament to the sophisticated design and engineering of JWST. The telescope's gold-plated mirrors, advanced detectors, and precise instrumentation work in concert to capture and analyze light with exceptional clarity and accuracy. Here is the text without skipping any words. As JWST continues its mission, the data it collects will undoubtedly revolutionize our understanding of exoplanets and their atmospheres. Each new observation adds to the growing body of knowledge, bringing us closer to answering fundamental questions about the formation, evolution, and potential habitability of planets beyond our solar system. The discoveries made by JWST will not only expand our knowledge of the cosmos but also inspire future generations of scientists and explorers to continue the quest for knowledge and understanding. The distinctive absorption patterns of atoms and molecules, combined with the advanced capabilities of the James Webb Space Telescope, have opened up new frontiers in exoplanet research. WASP-96b's spectrum, spanning an impressive range of wavelengths, provides unparalleled insights into the planet's atmospheric composition, temperature, and potential for habitability. As JWST continues to explore the cosmos, it promises to unveil even more astonishing discoveries, enhancing our comprehension of the universe and our place within it. Water and other essential molecules, like oxygen, methane, and carbon dioxide, which are not immediately apparent in the WASP-96b spectrum but should be detectable in other exoplanets, are particularly sensitive to this portion of the spectrum. Researchers will be able to measure the amount of water vapor in the atmosphere, constrain the abundance of different elements like carbon and oxygen, and estimate the temperature of the atmosphere with depth using the spectrum that Webb is planning to observe. They can use the data to draw conclusions about the planet's overall composition, as well as how, when, and where it formed. The best fit model, represented by the blue line on the graph, accounts for the data, the known characteristics of WASP 96b and its star, as well as the ascribed properties of the atmosphere. Modern web design has made it possible for these measurements to have such exceptional clarity and detail. The 270T gold-plated mirror effectively captures infrared light. Its sensitive infrared detectors detect incredibly minute variations in brightness, and its precise spectrographs disperse light into rainbows of thousands of infrared colors. NIRIs can distinguish brightness differences between colors that are a few hundred parts per million apart and color differences that are only a few thousandths of a micron apart. It covers infrared light wavelengths that we have never had access to before, which is exciting. The infrared atmospheres of exoplanets have been studied by other telescopes, but not with the same level of detail, and this is only a small portion of the data, according to Colin, an expert on exoplanets. In addition to Webb's extreme stability, its orbital location around L2 and its distance of about 1 million miles from the Earth's atmosphere allow for an uninterrupted view and quick data analysis. Only a glimpse of what Webb will bring to exoplanet research is shown by the incredibly detailed spectrum created by analyzing 280 individual spectra simultaneously. Researchers will use spectrography to examine the atmospheres of dozens of exoplanets, ranging in size from small rocky planets to giants that are abundant in gas and ice over the coming years. Exoplanet research and the materials it produces take up almost a quarter of JWST's cycle. In one observation, this closest observation demonstrates Webb's capability to describe exoplanet atmospheres, including those planets that may be habitable. The majority of the science, according to Antonella Nota, a JWST scientist who oversees the European Space Agency's office at the Space Telescope Science Institute, will be conducted using spectra. While we often say that a picture is worth 1,000 words, astronomers only consider spectra to be worth 1,000 pictures. And with that, today's episode comes to a close. We can only hope that the James Webb Space Telescope's enigmatic discoveries continue to surprise us with new information about exoplanets.